All right. In this video, we will work an example to practice with solving simultaneous mole and energy balances for CSTRs. So the example, an elementary liquid phase reaction, A goes to B, is carried out in a non-isothermal CSTR. Species A and an inert are fed to the reactor in equal molar amounts. The molar feed rate of A is 80 moles per minute. And then we're given some information about the different parameters involved in the reactor. And we're asked to solve for the reactor temperature for a feed temperature of 450 K, as well as the ignition and extinction temperatures. So I'll demonstrate what those are in a little bit. So first, let's derive the energy balance for this system, or derive the mole and energy balances. So we have a CSTR, it's non-isothermal. Coming in, we have species A and an inert. And we know what those flow rates are. The reaction is A goes to B. And coming out, we have A, B, and inert. The flow rate of the inert doesn't change because it's not reacting. And now that we have an energy balance, we're also going to worry about temperature. So we have some temperature coming in and some temperature coming out. And we also have a heat exchanger. And the heat exchanger has a constant temperature. The cooling fluid is a constant temperature, but it is going to exchange heat with the reactor contents. So first, let's do the energy balance. So you need to write a mole balance and an energy balance. Let's do the energy balance first. So this is a steady state system, so the accumulation term is going to be equal to 0. And then coming in, I have A and I. So I'm going to have FAO times HAO plus FIO times HIO. Coming out, I have AB and I, so I'm going to have FAHA, FB, HB, and FI, HI. I'm going to assume the work is 0 because I'm not given any information about what type of energy the stir is imparting. So I'm going to make that assumption. And now I have then just to worry about my Q term. So that's going to be my UA times my temperature difference, temperature of the coolant minus the temperature inside the reactor. And again, this is the order of these two temperatures is important. If this temperature is lower than this temperature, then the reactor contents are going to transfer heat to the cooling fluid. So this would be negative, and vice versa if TA is greater than T. So now I'm going to write in here a definition. So if I do that, then I get FA naught, HA naught, plus FI naught, HI naught, minus FA naught, 1 minus X, HA, minus FA naught, X, times HB, minus Fi naught, and this should be a naught here also, Hi, plus, actually I'll write this down here, plus UA delta T. So now I want to group terms. So once I have expanded terms and then I recollapse them, I'm going to group together these inlet enthalpy minus outlet enthalpy. So I have one of these for A and one of these for I. I'm also going to group terms that are multiplied by X. And then I have my heat exchanger term. This term is equal to negative heat of reaction So that's what I always want to fall out of my energy balance. These terms are the sensible heat changes. So these are going to be equal to a heat capacity times a delta T. So I can use all of this to simplify my energy balance. And so now I have a final form of my energy balance, which I can now solve for x, and I'm going to call that XEB. That's because I'm going to develop two equations. They're both going to be x of t equations. This one's going to remind me that this one came from my energy balance. I get this expression. Notice here that the negative sign on the heat of reaction has been removed. So here I have times a negative heat of reaction here. I have, since I subtracted this term over here, I changed the sign on this and then divided. The signs on everything else stayed the same. This is important because if the reaction is exothermic, then it gives off heat. So it's important to keep track of that sign. So this is my energy balance equation. So I can basically plot this for different values of T, and that would give me the solutions to my XEB. So combinations of X and T for this particular equation. But I have two unknowns. I don't know what X is and I don't know what T is, so I need another equation. For that I'm going to use the mole balance. So before I write down the mole balance, let me write down the rate law. So rate law. So we go back to our reaction. This is an elementary liquid phase reaction. A goes to B. So that means that minus RA is equal to KCA. And this is a situation, it's both liquid phase and there's no change in moles. So because of that, we can write this directly as a function of conversion without taking into account any volume changes. So that's going to be Ca naught 1 minus X times K. So now I don't have a value for Ca naught. I'm gonna take care of that in just a moment, however. So my mole balance for a CSTR is equal to B is equal to Fa naught X divided by minus Ra. So I can substitute my rate expression into there. So now I notice that I have these two constants. I have Fa naught divided by C naught, or Ca naught. So this is actually going to give me a volumetric flow rate. So that's going to be V naught times X divided by K times 1 minus X. And then what I want to do is I'm given this value here for the residence time tau. So if I divide both sides by this, the volumetric flow rate, I can solve in terms of tau. So I get tau is equal to X over K 1 minus X. And again, what I want to do is solve this equation in terms of X. So if I do that, so let's simplify this down. So if I do this simplification, or if I do this rearrangement, this is how the equation I get for X. It's now in terms of tau and K. So that gives me my second equation, XMB, because this is from the mole balance, equals tau K divided by 1 plus tau K. And I have everything now given to me that I need to solve the problem. What I'm going to do is I have two equations, my energy balance and my mole balance. I have two unknowns, X and T. I am going to solve these. I can do this a variety of different ways. A popular way to do it is to do it graphically. I'm going to actually work this problem in Microsoft Excel. I think maybe some of you will enjoy that. Of course, I could do it in Python also, or a variety of other software. But in the next video, I'll show you how I'm going to solve this in Microsoft Excel.